In this video I make the bold claim that the normal distribution, this bell-shaped probability distribution that is supposed to appear, well, everywhere, actually doesn't exist. So what do I mean by that? In every statistics class we learn about the importance of the normal distribution. It appears in features of the human body and personality, like height or IQ, in technical processes, for example in measurement errors, and of course in economy. So how can I claim that there is no normal distribution? To get a better grip on the topic, we first need to understand what the normal distribution is. The normal distribution gives us the probability distribution of many phenomena that we encounter in our daily lives. It is given by a so-called bell curve or Gaussian curve that in its standard form is given by the following formula. It has its maximal value exactly in the middle, it is symmetrical, and it goes to zero quite fast as soon as we go farther away from the center. Of course, if I say that the normal distribution doesn't exist in reality, I mean it in a very rigorous sense. So, my first argument why the normal distribution doesn't exist is the fact that the function is continuous and it has non-zero values for all real numbers x, which means that the curve spreads out on the whole x-axis all the way up to plus and minus infinity. In real-world data, however, nothing is spread out over an infinitely large domain, and no data set is actually continuous, but it rather consists of a discrete amount of data points. If we accept that the universe is finite and that the number of particles in the universe is finite, there really is no way to argue on this specific fact. So instead of this, we would rather have this. This is really the main issue I have with the normal distribution, because in order to work properly, it would require an infinitely large amount of information. But in order to get a better intuition on the problem, we have to dig a bit deeper. Alright, why is the normal distribution so essential in statistics? It all has to do with the central limit theorem. Imagine you have an arbitrary distribution. It can take any shape or form as long as it fulfills some basic conditions on its mean value and standard deviation. There are several versions of the theorem, but one of them simply requires the mean and standard deviation to be finite. And yes, even if it sounds a bit silly at first, there are probability distributions where those values are in fact infinitely large. Let's take for example a so-called power law, which is a distribution that is given by a rational function with a monomial in the denominator. Its mean is finite, so no problem here. But we can clearly see that the variance is infinite. In this integral we only care about the term with the highest power of x, so we ignore the rest. In the leading term we are left with the integral of 2 over x, which is basically a logarithmic function that goes to infinity for large x. Distributions like this are in fact quite relevant in real-world applications. Power law distributions, which are also called Pareto distributions, are for example used in economics. However, most of the simpler distributions, especially those where the sample space is finite, don't have such odd properties. So let's get back to the central limit theorem. Let's say we have such a distribution with nice properties like the probability for a die roll. Here we have a mean value of 3.5 and a standard deviation of about 1.7. Now imagine that we make lots and lots of measurements that follow this probability distribution and all the measurements are independent of each other. In this example, it means we throw a die several times in a row. Now we take the sum of all those measurements. Of course, if we throw 2 dice and add their values together, the shape of the distribution changes because it's much more likely to throw 7 than a 12. The central limit theorem now states that the more iterations we do in this experiment, the more we tend towards a normal distribution. Every time that we sum up the results of independent repetitions of a measurement, we get something that tends towards a normal distribution as the number of repetitions gets larger. Why? This is an interesting question that I don't want to answer here, because there is a really good video by 3 Blue 1 Brown that covers this question elaborately. If you're interested, you find the link to this video in the description box. We want to answer another question. Why can we apply the theorem to so many real-world phenomena? We start with an easy example. Let's think about taking a maths exam in school. It is often said that the perfect test score for a classroom should be normally distributed. But why? Let's say the test contains 10 questions and Alice knows about 80% of the topics that were discussed in class. This means that for each question she has an 80% chance to answer it correctly. So for every question we have a random variable xi that tells us if Alice answered the ith question correctly. All those xi are independent of each other, given that the 10 questions can be answered each on their own. If we add them up, we get the random variable that corresponds to Alice's final test score. The expected value for each xi is 0.8 and the standard deviation is 0.4, so both are finite. This means that the preconditions of the central limit theorem are fulfilled. Hence, if Alice would take multiple tests on the same topic, the number of correctly answered questions can be approximated by a normal distribution with mean 8 and standard deviation 1.26. If we look at a simulation, we can see how the shape of the bell curve is coming about. But wait a minute. This simulation is taking into account only the probability for Alice's test score, not the whole class. Well, for Alice's classmates it should be similar, although their individual chances for each question might be different depending on their personal effort. The distribution for the whole class can be obtained by the sum of different normally distributed random variables with different means and standard deviations. But the sum of those is still normally distributed, as long as they're independent of each other. Nice. So we had our first example. But what about a second example? Now let's consider something more complex, like the height of a certain species. To make the maths a bit easier, we look at a simplified model. Let's imagine we start with a population of 10 individuals of a certain species. We make the following assumptions. All 10 individuals of the first generation have the size 1 meter or 100 centimeter if you will. Each individual creates 2 offspring without another creature being involved. Each child has the same height as the parent or is 1 centimeter larger or smaller with a probability of 1/3 in each case. Of course, this simulation is a heavily reduced model of reality, but it should give us a fundamental intuition of what is happening here. To show that we created an example where the central limit theorem is applicable, we have to write down some formulas. The probability distribution that we talk about is the distribution where we have -1, 0 and 1 in 1/3 of all cases respectively. The mean value of this distribution is 0 and its standard deviation is the square root of 2/3. So everything is finite. Okay, but we're still waiting for the sum. Where is it? Well, in many cases, the data that shows a normal distribution was shaped over time with many iterations of little changes that finally added up to the form that we can now observe. In this case, it means that we have to consider the evolution of the species from one generation to the next. If the creatures in the first generation have children, the height of a child in the second generation will be 100 plus x1, where x1 is a value that we have chosen from this distribution. The height of children in the third generation is 100 plus x1 plus x2, where x1 and x2 are independent measurements in the underlying distribution. In the fourth generation, it will be 100 plus x1 plus x2 plus x3. And in the nth generation, we can write the height of a child as the following sum. Finally, we can see that the conditions of the central limit theorem are truly fulfilled. If we let our simulation run, we get the following result, which after a certain amount of time looks quite bell-shaped. Now you might say that a more realistic model for the evolution of a human population would have other properties that might not suffice the conditions of the central limit theorem. For example, there is a phenomenon which we call regression to the mean, which says that the chances for a child to be taller than its parents shrinks as the parents get taller themselves. This means that the value xn is not independent of the values of xi for I less than n. This would violate the preconditions of the theorem, at least in the form as it was stated earlier. On the other hand, I also told you that there are several versions of the central limit theorem, even some where the iterations don't have to be stochastically independent. And the fact that we can write the height of a member in the nth generation as the sum of random variables stays the same even in this modified situation. Alright, the second example was a bit more complicated, but it shows us how in many cases the sequence of random events that led to the normal distribution is hidden in the time evolution of the system. Creating a model where we see the sum of random variables can be tricky, but it gives us a nice intuition for the data. So is this our final conclusion? Well, there is one more thing I would like to talk about, but first let's add a tiny detail to our population height model. While constant growth rates give us an easy model and a solid intuition of what is going on in the evolution of our hypothetical species, most things in nature that involve growth behave a little bit differently. Let's assume we want to apply our growth model to another type of animal, where the individuals in the first generation are 5 centimeters large. Now we probably wouldn't use the exact same model where children can differ up to 1 centimeter in size from their parents. In fact, what we usually find in nature is that size differences from one generation to the next are somehow relative to the actual size of the parents. So, instead of choosing a new set of fixed values for our distribution xi, we could simply modify the whole model and say that the height difference of a child to its parent can be either 0 or plus 1% or minus 1% relative to the height of the parent. But how different are both models actually? Maybe not so much. We can still use the same probability distribution where we draw our random number xi from the set -1, 0 and 1, but now the formula for the height of the second generation changes to h1, which is the initial height of the parents in the first generation, times 1 plus x1 over 100. In the fourth generation, we have the formula h1 times 1 plus x1 over 100 times 1 plus x2 over 100 times 1 plus x3 over 100. And in the nth generation, we can write it as the following product. Now the sum is gone and we have a product of many random variables instead. The central limit theorem is no longer applicable, but if we let the simulation run, we encounter something that still reminds us of the well-known picture. This shouldn't surprise us. As long as we have only a few iterations, we still have kind of the same mathematics. If we expand the term for the second generation, we get the following sum, where the mixed term with the denominator 10,000 is so small that we can treat it as if it's not even there. With h1 equals 100, our sum takes almost the same shape as in our initial model. But in the long run, as we get more and more multiplications, this small deviation makes a huge difference. As we said, the central limit theorem doesn't apply anymore since the sum is gone. However, there's also a multiplicative version of the theorem. If we have independent measurements that are multiplied instead of added, or, in the words of our species model, if we have a growth rate that is relative to the height of the parents, then our distribution tends towards the so-called logarithmic normal distribution or log-normal distribution. We can get the normal distribution out of the log-normal distribution if we take the logarithms of the distribution's values. It is skewed to the right and therefore not symmetrical. This is due to the fact that the relative growth of a quantity is larger if the quantity itself is already large. And the log-normal distribution is truly everywhere. Animal sizes across different species, household income, population of cities, size of celestial bodies, all those numbers follow the log-normal distribution. In most cases, things grow relative to their current size. If a planet is already large, its capacity to become larger by accumulating matter is increased. If a city is large, its capacity to grow by birth rate or by migration is higher than that of a small city that nobody has ever heard about. It is quite likely that most of the distributions that you think are normally distributed actually are log-normal. In addition, the log-normal distribution has the incredibly useful property that its x-values must be positive, which means that the domain is bounded from below. Many things that we measure don't take negative values. So, are you convinced? There is no normal distribution in real life. Real-life data is discrete anyway, so continuous probability distributions are rather a scientific model to work with than an actually existing thing. And even if you talk about models, it is quite likely that the normal distribution you talk about is, in reality, something completely different, like a log-normal distribution. I hope you enjoyed the video, learned something new, and hopefully gained a little intuition about probability distributions and the laws of nature. Until next time.